Okay, let's unpack this. We all love that feeling, right? Stepping into a cool building when it's absolutely scorching outside. But have you ever really stopped to think about the cost? Not just, the electricity bill, but the environmental cost. Today, we're doing a deep dive into some really fascinating research. It kind of pulls back the curtain on something maybe we don't think about enough.
Yeah.
The insulation inside our walls.
Yeah, exactly. We're looking at this great study by Al-Sakabi and his colleagues. It was published in Buildings back in 2023, and it specifically looks at the challenges in hot, dry places like Saudi Arabia, places where keeping buildings comfortable can use up, believe it or not, maybe 60% of the entire country's energy.
60%. That's staggering.
It's huge, a
Oh, okay.
massive energy sink.
And here's where it gets, I think, really interesting for you listening. They didn't just look at, how well different types of insulation stop heat. They went this crucial step further. They brought in something called life cycle assessment, LCA. Sure. So our mission today is basically figuring out how we can stay cool and be kinder to the planet. And we're going to use some pretty surprising facts about what's actually in our walls to do it. Okay, so let's set the scene a bit more. Globally, buildings are just, well, they're huge energy consumers. About 40% of primary energy just for heating and cooling. But in those hot, dry areas, like the Qasim region in Saudi Arabia they studied, the numbers are even starker. Get this. Over 65% of the yearly energy for a typical house without insulation goes just to air conditioning.
That's right. It's just an unsustainable level of demand. And this isn't only about comfort, it's a major sustainability issue. Saudi Arabia has this big plan, Vision 2030, and energy efficiency is a huge part of it. Now, a lot of effort has gone into things like efficient appliances, which is great, but there's this growing awareness that you have to look at the building itself. The walls, the roof, the windows, the whole envelope. That's where the big wins are.
Right. It makes you think, doesn't it?
Yeah.
How much are our buildings just fighting the climate instead of sort of working with it? And we know from other studies that improving that building envelope, it can save a lot of energy, maybe, what, 20, 30, even close to 40%, depending on the city.
Exactly. Those savings are significant.
But here's the twist, the thing this study really digs into. Just piling on more insulation isn't automatically the best answer. Why?
Well, because making that insulation, that process has its own environmental footprint. There's an embodied energy cost, an embodied carbon cost.
Ah, okay. So you save energy running the building,
Right.
but you spend energy and resources making this stuff in the first place.
Precisely. And that's why this study on the Qasim region is so important. It really tries to look at that whole picture, filling a gap in the research. So how did they do this deep dive? They focused on 288 residential villas at Qasim University. They were all pretty similar, which made it a great real-world lab. And the climate there, it's intense. Average summer temps can hit 46 Celsius. That's like 115 Fahrenheit.
Wow.
But then winter nights can drop below freezing, and you've got very high solar radiation too. So a really tough environment for buildings.
Okay, huge temperature swing. So how did they actually measure what was going on? How did they get the data?
They use these things called HOBO data loggers, little devices that track the indoor temperatures in the actual villas,
Wow.
real-world data. And then they took that data and used it to build and, importantly, validate their computer models. They used software, IESVE, which is pretty standard for this kind of simulation.
And how well did the computer models match the real world? That's always the key question, isn't it?
It really is. And they did well. They found a strong correlation. The R-squared value was 0.81.
0.81. So for anyone not deep into stats, that basically means the model explained about 81% of what they actually measured.
Yeah, that's a good way to put it. It's a very strong sign that their simulations were accurate, really robust.
Okay, great. So they have this reliable model. What insulation materials were they actually comparing?
They looked at four common ones: XPS, that's extruded polystyrene,
Hmm.
EPS, expanded polystyrene, then Rockwool, RW, and Glasswool, GW.
And crucially, they didn't just simulate how well these kept the heat out. They did that life cycle assessment, the LCA.
Exactly, using SimaPro software. And they focused on what's called the cradle-to-gate phase.
Cradle to gate, meaning
Meaning from like digging the raw materials out of the ground all the way through manufacturing until the finished insulation product is ready to leave the factory gate before it even gets shipped to a construction site. And they measured the impact primarily in terms of global warming potential, or GWP. Basically, it's carbon footprint measured in kilograms of CO2 equivalent.
got it. So you've got the thermal side, how well it insulates, and the environmental side, how much carbon it took to make it.
Right.
Okay, with all that groundwork laid, What did they find? What were the big surprises in terms of keeping buildings cool? You'd think, okay, more insulation, lower U value, better cooling. Simple, right?
Well, yes and no. Generally, a lower U value is better. That's true. Thicker insulation usually means better thermal performance.
Got it.
But, and this is a big but, the building's orientation turned out to be massively important.
Orientation, like which way the wall is facing.
Exactly. Their simulations showed very consistently that the walls facing south always had the highest cooling loads, no matter which insulation they tested.
Huh. Okay, so the sun hitting that south wall really makes a difference.
A huge difference. And what that implies is that maybe a single standard thickness recommendation, like you might find in a building code, isn't the smartest way to do it. A one-size-fits-all approach might be inefficient.
Right, because a north-facing wall just isn't getting hammered by the sun in the same way.
Precisely.
So let's take an example. You mentioned the Saudi building code, SBC 602. Maybe it suggests, say, 80 millimeters of XPS. What did the study find about applying that everywhere?
Well, that 80 millimeter XPS might be just right for the south-facing wall to hit the performance target they were using, which was 151 kilowatt hours per square meter. But the study found for the north and west walls, you could actually use less, maybe only 70 millimeters of that same XPS. Or you could even switch to 75 millimeters of Rockwool and still meet or even beat the code's thermal limits for those walls.
Ah, so you actually tailor the insulation. Thicker on the south, maybe a bit thinner, or a different type on the north and west.
Exactly. And doing that, strategically adjusting thickness based on orientation, could lead to some pretty significant cuts in the overall cooling needed, without actually sacrificing comfort or falling foul of the regulations.
That's a really powerful insight just on the thermal side. But then you bring in the LCA, the environmental footprint.
Yes. And this is where the study, I think, really delivers its punch. When they calculated the GWP, the carbon emissions from making these materials,
Wow.
the differences were huge. A really clear hierarchy just jumped out in terms of which materials were, let's say, greener to produce.
Okay, I'm ready for the ranking. Lay it on us. Who was the worst offender, environmentally speaking?
The highest emitter by far was XPS, the extruded polystyrene. It came in at 5.28 kilograms of CO2 equivalent per unit they measured.
Okay, XPS at the top. Who's next?
Next was glass wool, GW, at 3.2 kilos. Then came EPS, the expanded polystyrene, pretty close behind at 2.9 kilos.
All right, so XPS is way out in front. Then Glasswool and EPS are sort of middle of the road. Who was the winner? The lowest footprint?
The clear winner was Rockwool. RW, its GWP was just 1.3 kilograms of CO2 equivalent.
Whoa, hold on. 1.3 for Rockwool versus 5.28 for XPS.
That's right. It means Rockwool has an astonishingly lower GWP. It's about, 300% less GWP than XPS.
300%. That's not a small difference. That's enormous.
No.
Why? What makes XPS so much more carbon intensive to produce than Rockwool?
It comes down largely to the manufacturing process, especially the blowing agents they use to create the foam structure. XPS often uses things like HFCs, hydrofluorocarbons, which are unfortunately very potent greenhouse gases themselves.
Ah, okay, so the stuff they use to puff it up is actually bad for the climate.
Essentially, yes. Whereas EPS, the expanded one, often uses just water vapor. Much cleaner from a GWP perspective. And Rockwool, well, it's mostly made from natural rock, basalt, and recycled slag. While it takes energy to melt and spin it, the raw materials in the process overall lead to that much lower GWP.
That makes a lot of sense. So the process really matters. And there's another detail, too, about density, wasn't there? That seems surprising.
Yes, density played a big role too, which you might not immediately think about. Higher density generally means more material and thus a higher environmental impact to produce it. They showed an example with XPS. At a lower density, maybe 21 kilograms per cubic meter for an 80 millimeter board, the total CO2 equivalent was around 442 kilos. But if you used a higher density XPS, say 48 kilos per cubic meter, that number jumped way up to over 1,000 kilos of CO2 equivalent.
Doubled it almost, just by using a denser version of the same material.
Exactly. It's a critical factor. Now, density affects the GWP for all the materials, but the key finding was that Rockwool still came out with the lowest emissions across its typical density range. It just consistently performed better on that environmental metric.
Okay, so let's try and connect these dots. We've got thermal performance, which depends on thickness and orientation, and we've got environmental footprint, GWP, which depends on the material type and its density.
Precisely. And what this research really gives us is a framework, a tool for optimizing our choices. It shows that we shouldn't just look at one factor in isolation. It's not only about getting the lowest U value, the best insulation effect, and it's not only about picking the material with the lowest GWP, it's about finding the sweet spot between them.
That's a balancing act, isn't it? A multivariable optimization, really.
You could definitely call it that.
So, for you listening, imagine designing a building now. You could, using this kind of data, strategically choose which insulation to put where. Maybe rock wool on the north and west walls, perhaps at a slightly lower thickness than code minimum if performance allows. And maybe on the south wall, you still need something thicker, perhaps even a different material if rock wool doesn't quite cut it thermally there. But you're making that choice consciously, knowing the GWP trade-off.
Exactly. It allows for a much more nuanced, customized approach.
And the end result is potentially a building that performs really well thermally, keeps people comfortable, uses less energy for cooling, and has a significantly lower embodied carbon footprint from the materials used to build it. That's like a huge win-win.
It really does offer a path towards those kinds of powerful sustainability benefits.
So wrapping this up, what's the big takeaway for us? What does this all mean? For me, it's a reminder that, real efficiency, real sustainability, it's often hidden in the details. It's about understanding these complex interactions, design, materials, the specific environment. We can actually move beyond just following blanket rules and start creating buildings that are genuinely optimized, smarter, not just more insulated.
Absolutely. This study really hammers home that picking insulation isn't just about checking the R value on the packaging or meeting a generic code requirement. It demands a more holistic view, a life cycle perspective. You got to think about everything from how it's made to how it performs over decades to the energy it saves.
Okay, so here's a final thought for you to maybe mull over after this. If optimizing just the insulation based on orientation and material choice could have this much impact on energy and carbon in one specific region, what else are we missing? What other common building materials or maybe even construction practices could benefit from this kind of deep dive? Where else might we find these hidden footprints, these unexpected ways to build a much more sustainable future? We'll definitely keep unpacking questions like these right here on The Deep Dive.